So it's a typical question about the magnet field, and we can get enough information from the question itself. Firstly, this 110 means the parameter n is with a value of 100, and we get the diameter of this circle, which is 10 centimeters. So apparently, we can get the parameter of this circle, and we can also get the area cross-section area A, which is 5 centimeters. And finally, it is asking us to calculate the inductance. So from the very beginning, we start from the definition of inductance, which is phi divided by I. Okay, phi is a magnetic flux. Please remember this table I'm going to write. This is electric the area. This is a magnetic area. This is about flux. This is about flux density. This is about field intensity. Okay, so the electric flux is psi. Magnetic flux is phi. Electric flux density is D. Magnetic flux density is B. And finally, electric field intensity is E, and the magnetic field intensity is H. The relationships between those things is D equals psi divided by A. A is the cross-section area. B equals phi divided by A, and D also equals permittivity times E, and B equals permeability times H. Remember all these things, it will be very helpful to you in the future. And now we know if we get the value of phi and I, we can get the value of L. So we don't know neither of them, but we know from the table phi equals B times A. We know the value of A. A equals 5 times minus 10 power to minus 4 square meters. If we get the value of B, we will get the value of phi. So how to get the value of B? This is the equation about magnetic field, about the magnetic flux density, about the current. So we must have to remember the law of Ampere, Ampere's law, right? One of the pole of the Maxwell equations. So which is H dl equals the total current. So this symbol of integration is about, one-dimensional closed loop integration, which means you have a curve with any shape, but it must be closed loop. So the integration root is running along the edge of this curve. And because it's a closed one-dimension curve, it will enclose an area of two-dimensional. So the total current that running in this two-dimensional area is this current. All right. So we can easily solve this equation, which is H times 2 pi r equals Ni. All right, because our magnetic material is a circle, so we use a parameter to work as a closed one-dimension curve. All right, so H is B divided by mu equals Ni divided by 2 pi r. All right, so B equals mu r times mu 0 Ni divided by 2 d divided by 2, half of the diameter. Okay, we can move it simpler like this. Okay, we get the expression of magnetic flux density, we will get the phi, which is B times A, which is mu r mu 0 Ni A divided by pi d. Alright, and finally, we can directly get the value of inductance, which is I divided by phi divided by I. But remember, this I is the current that is flowing inside one single wire, which means it's phi divided by I divided by M. It's not the current in the coil, it's the current in the single wire. So we can get the final result, which is like this: mu r mu 0 n square I times A divided by I times pi d. Oh, okay, the lucky thing is we can remove this I, okay, and the d, we just input every value inside. It's 750 times 4 pi 10 power the minus 7 times 10 times 4, which is n square, and phi. The area is 5 times 10 power the minus 4, because we have to convert the unit from square centimeter to square meters, right? And this is pi times d, which d is 10 times 10 minus 2. Okay, so we just solve this problem and solve this equation, which can be easily calculated because the pi can be removed, right? It will be the 15 millihenry. That's the final answer. Thank you, everyone. Have a good day. Bye bye.